As we're beginning to see, statistics sharpens our knowledge of how randomness is all around us. Life is full of having to make decisions under uncertainty. In fact, the two fundamental ideas of statistics are uncertainty and variation. Now, in some cases, the uncertainty is because the outcome in question hasn't been determined yet. Like, who will win the next Super Bowl? My money's on the Atlanta Falcons because I'm from Georgia. But in other cases, the uncertainty is because although the outcome has been determined already, we're not aware of it. Like whether or not our application for a car loan has been approved. Now, probability is the foundation that helps us understand uncertainty and variation. And that's why probability plays a key role in statistics. By definition, probability is a mathematical language that we use to measure uncertain events. Now, whenever we collect data or make measurements, the process that we use is subject to variation, meaning if the same measurements were repeated, the answer would be slightly different due to variation. So what is this data that we're collecting anyway? Well, one way to think of it is data is the raw information from which statistics are created. Data is being collected everywhere, all the time. And when we collect data, what we're doing is really converting information into numbers. But what do we do with those numbers? Well, statistical thinking gives you the tools to intelligently extract information from data. It's helpful to think about data collection in the context of the general process of investigation. Step 1, we state the question that we're interested in. So maybe we want to know whether drinking caffeinated beverages affects men differently than women, or if a new cold medicine will relieve coughing within 48 hours. Whatever the question is, we need to be able to gather information that'll help us make a decision. And that's step 2. Collect data that helps answer the question. Okay, back to our cold medicine example. Suppose I give some samples of cold medicine to my coughing friends, and you give some to your coughing friends, and we record how many of them stop coughing within the 48-hour period. We've collected data. Now what? Well, do you think we're ready to move on? Not quite. You see, what we've just introduced is a bias, and we put that into our data. It's likely that our close friends have similar characteristics as we do. Maybe they're in our same age bracket, or they live in the same city. In my case, most of them are women. So in order for our results to be widely applicable, we have to collect data in a way that's objective and rigorous. One improvement, we could stand in front of a drugstore and sample people as they go in and out. Another, perhaps, might be to call random numbers from a phone book and ask people to participate in our trial. But both of these methods are still biased. If we're sampling only from a particular group, then our results will only apply to that group. If we want to remove bias entirely, we have to collect a sample where every person has an equal chance of being selected. Now, once we've stated the question and collected appropriate data, we can move to step 3, which is analyze the data. This is where we really begin to see the ideas of probability and statistics take shape, literally. Statisticians often start an analysis with a graphical look at the data to get an overall picture of it. We use plots, graphs, tables, anything that can help us reveal patterns or relationships within our data. Now, a plot or a graph can be a more effective way of presenting data than just a mass of numbers, because we can see where the data is clustered and where there's only a few data values. Then we could also use formal techniques like hypothesis testing or linear regression to determine if or how much our data supports our initial claim. Ultimately, we want to use our analysis to make a decision about our problem statement, which leads us to step 4. In the last step, we draw a conclusion. Here we consider all the information that we've gathered, and we analyzed, and we make a definitive statement about our problem. Something like, study shows that new miracle cough medicine relieves coughing in 48 hours, guaranteed. How's that sound? All right, well, that conclusion's too strong. In fact, a conclusion with zero uncertainty is really too good to be true. But we do want to extend the results from our sample data, the data that we collected, to the overall population more generally. This lesson is going to give you a strong foundation in probabilistic reasoning and the basic tools needed to make sense of it all. We first start with sampling, which refers to selecting at random one or more of all possible outcomes. So for example, selecting a random sample of Americans for a political poll. Or maybe even drawing a hand of 5 cards out of a deck of 52. Or finding 10 pennies on the sidewalk and recording their ages. Sampling helps us draw inference about the larger population of outcomes. Now, drawing random samples forms the foundation of probability, which is all about considering the possible outcomes of an experiment and quantifying their chances. How many of us have ever heard a weather forecaster declare, "There's a 75% chance of rain today"? Well, what this really means is that in a large number of days with atmospheric conditions like those today, the proportion of days in which rain occurs is 75%. So why then does probability refer to the long run? Well, it's simply because we can't accurately determine a probability with a small number of observations. If I sample 10 people and they're all right-handed, I can't conclude that, probability of being right-handed is 100%. It takes a much larger sample of people to accurately predict the proportion of people that are truly right-handed. So what happens when we have real but limited data and we want to make a conclusion from it, maybe calculate some probabilities? We don't have time to go in the long run, so what do we do with this limited sample size? Well, here's an example in that case. Suppose we wanted to understand how a grocery store displays their cereal boxes and whether different types of cereals are targeted to adults or children. We go into a grocery store and we notice that there are 6 rows of shelves, and each shelf has 5 boxes of cereal. We can group the 6 shelves into 3 categories: the bottom 2 shelves, the middle 2 shelves, and the top 2 shelves. Here's a look at that data now. Notice in the first column, we have adults, children, and the total. The second column tells us how many boxes of cereal are located on the top 2 shelves. So 9 boxes are targeted at adults, 1 for children, for a total of 10 boxes. Likewise, in the middle 2 shelves, 3 boxes of cereals are targeted at adults, 7 for children, and a total of 10. And then you see the bottom 2, no boxes targeted at adults, 10 for children out of a total of 10. The farmost right column total is going to add up the total number of boxes that are targeted at adults, which is 12, and targeted at children, which is 18. Suppose we wanted to know the probability that breakfast cereal is targeted at adults. Let's call this event A. Well, the probability of A would be 12, which is the total number targeted at adults, out of 30, which is the total number of cereal boxes, or 40%. Now we could do the same type of calculation and determine the probability of breakfast cereal being in the middle 2 rows, for instance. Let's call that B. The probability of B would be 10 out of 30, or 0.33. Now it's natural to think about how 2 events relate to each other. For example, what's the probability that the cereal is targeted at adults and located on the middle 2 shelves? Now, in this case, we want to look at our data to see where those 2 events occurred together. Notice that 3 types of breakfast cereals are located in the middle 2 shelves and targeted at adults. So our probability would be 3 over 30. Now, we use this upside down U to refer to the intersection, or the place where 2 events overlap. So the probability of A intersect B is equal to 10%. or 0.1. Now, what if we were interested in knowing the probability of A or B? Probability that cereal is targeted at adults or is located on the middle two shelves. In this case, we're no longer limited to just the intersection. The cereal could be targeted at adults with probability 12 over 30, or located on the middle two shelves with probability 10 over 30. So it makes sense for us to add these two probabilities. The probability of A union B equals 12 over 30 plus 10 over 30. But do you see a problem here? Notice that by adding the probability of A plus the probability of B, we've included their intersection twice. We need to subtract one of those back out. So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of their intersection. So 12 over 30 plus 10 over 30 minus 3 over 30 to give us 0.63 or 19 over 30. Now, if you've ever visited beautiful, sunny Southern California, you'll have noticed that there's one thing that we have very little of, and it's rain. In fact, and this is a true story that my husband probably wouldn't want me to share with you. I remember once when the windshield wipers on our car malfunctioned and they stopped working completely. And we went 7 months without getting them fixed, simply because there was no rain event significant for us to need to use them. I'm sure that'll stay between the two of us. But now suppose one morning I walk outside and I see dark clouds in the sky. Well, all of a sudden the probability of rain, at least to me, has now increased. What I've just done is updated my belief about rain, having seen dark clouds in the sky. Likewise, we could update our probability of events by conditioning on new given information. Let's go back to our cereal example and define a new event. Let C be the event that cereal is targeted to children. What's the probability of C? Well, that's 18 out of 30, or 60%. So there's a 60% chance that cereal is targeted toward children. What's the probability of C and B? Well, remember, B is the event that cereal is located on the middle two shelves. Well, here again, we're looking at the overlap or the intersection of these two events. So the probability of C intersect B is 7 out of 30, or 0.23. Now, what is the probability that cereal is targeted to children given that it's located on the middle two shelves? This question is asking, what's the probability of event C given the information from event B? So now we write the probability of C given B, which is what that slash represents, which is 7 out of 10, or 70%. We've limited ourselves to the middle two shelves, and of those 10 boxes of cereal, we see that 7 of them are targeted to children. So our conditional probability was actually higher. Let's add some formal definitions to what we just learned in that example. First, an experiment. This is an action whose outcome is uncertain. Examples might be flipping a fair coin or rolling a fair die twice. From experiments, we can build a sample space. This is the set of all possible outcomes of that experiment. In our flipping a coin example, our sample space S would be equal to either H for heads or T for tails. Likewise, if we're rolling a fair die twice, our sample space are all possible combinations of those two rolls. So we might roll 1 and 1, 1 and 2, all the way up to 6, 5, and 6, 6, and everything in between. We define an event as a collection of outcomes of our experiment. If we flip a fair coin, for example, the event might be that we flip a head. Or in our rolling a fair die, maybe we define an event as the sum equals 4, in which case there are 3 possibilities, 1 and 3, 2 and 2, or 3 and 1. So from these events, we want to associate a probability to them. A probability is just a rule that assigns each event a value on the interval from 0 to 1 that's going to reflect the chance of that event occurring. Now, when all the outcomes in the sample space are equally likely, the probability of event is just the number of outcomes corresponding to that event, divided by the total number of outcomes. Let's go back to flipping a fair coin. What's the probability that we flip a head? We probably know that's 1/2, but we get that by taking the number of events in flipping a head, which is H, or one event, out of the total number of possible events, which is 2. Likewise, if we roll a fair die twice, the probability that the sum equals 4 equals those 3 events out of the total 36 possibilities, so 3/36. Now, the building blocks of statistics are what we call the axioms of probability. These are the beginning statements that are the ground rules from which we build and prove statistical theory. We can reduce probability theory to just 3 fundamental axioms. Let's talk about them now. The first one is this. For any event A, the probability of A is between 0 and 1. The smallest the probability can be is 0, so we can't have any negative values associated with probability. Likewise, the largest it can be is 1. The second axiom tells us this. If S is the sample space, the probability of the sample space is equal to 1. Also, the empty set, which is everything that's not in the sample space, is equal to 0. So the probability of our empty set, or no event, is equal to 0. The sample space is everything possible for our experiment, and there are no events that live outside of that space. Now, the third axiom of probability deals with mutually exclusive events. But first, we need to understand unions and intersections formally. A union, the probability of A or B, is denoted by probability of A union B, or a U sign. Likewise, the intersection is the probability of both A and B, and we denote that as P of A intersect B, or an upside down U. Now, if A and B are mutually exclusive, meaning they don't overlap or they don't intersect with each other, then if we wanted to get the probability of their union, it's just the sum of those probabilities. So P of A union B is equal to P of A plus P of B. Now, what about the probability of A not happening? We actually have a word for this, A complement. It's the probability of A complement is 1 minus the probability of A. More formally, if we're looking at the probability of a union of events, we saw in our example that the probability of A union B equals the probability of A plus the probability of B minus the probability of their intersection. Now, if they're mutually exclusive, the intersection has probability 0, which leads us to the last one. If A and B are independent, the probability of their union is the product of their 2 probabilities. Now, this leads us to the idea of conditional probability. Knowing that the cereal is located on the middle 2 shelves now changes the probability of being targeted to children. More formally, let's let A and B be events where probability of B has positive probability. Then the conditional probability of A, given that B has occurred, is defined as the following. P of A given B is equal to the probability of A intersected with B divided by the probability of B. Now, if we go back to our example, we could actually calculate the probability of C given B, now using our formal definition. Another way to view conditional probability is by solving for the intersection term. We can rewrite our definition as follows. The probability of A intersect B is equal to the conditional probability of A given B times the probability of B. All right, so now the probability of A and B occurring, well, that's the same as the probability of B and A occurring. So we could write that slightly differently. Probability of A intersect B is P of B given A times P of A. We could set these 2 equations equal to each other to get P of A given B times P of B equals P of B given A times P of A. All right, now at first sight, it might not seem very useful. In fact, it seems pretty circular that we've just rewritten the probability of A and B and probability of B and A and set them equal to each other. But if you divide both sides by the probability of B, what you're left with is an extremely famous, extremely useful result that relates conditional probabilities and is known as Bayes' rule. Bayes' rule simply states that the probability of A given B equals the probability of B given A times P of A divided by P of B. Let's take that denominator, and in fact, we can expand it using what we call the law of total probability. We can write out the probability of B as the probability of B intersected with A plus the probability of B intersected with A complement. We showed where that intersection could be written as a conditional probability, so we can further dissect that into the probability of B given A times P of A plus the probability of B given A complement times the probability of A complement. Put that on your denominator and you'll see another form of Bayes' rule, where we can write the conditional probability of A given B as P of B given A times P of A all over the sum of P of B given A times P of A plus P of B given A complement times P of A complement. Now, Bayes' rule is a powerful tool that we can use, and it can actually help you in everyday life. Suppose you're worried that you might have a rare disease. You visit your doctor and get tested, and she tells you the test is accurate 98% of the time. So if you have the rare disease, it'll correctly tell you that you have it 98% of the time. Likewise, if you don't have the disease, it'll correctly tell you that you don't have it 98% of the time. Now, this disease is rare and is deadly, and it occurs in only 1 of every 10,000 people. Unfortunately, your test result is positive. Well, what's the chance that you actually have the disease? Some people guess this probability is around 98%. But Bayes' theorem is going to help us answer this question. Let's define an event A, where we have the disease, and the event B that the test is positive. We want to know, what's the probability of A given B? What's the probability that I have the disease given that my test is positive? Well, I don't know that, but I can use Bayes' rule to solve for it. First, let's write out what we do know. The probability of B given A, probability that the test is positive, given that we have the disease, is 0.98 or 98%. Likewise, the probability of the disease is 1 in 10,000 or 0.0001. The probability of B given A complement, that the test is positive given that we don't have the disease, is 0.02. And the probability of not having the disease or A complement is 1 minus P of A, or 0.9999. So from here, we can plug this into Bayes' rule to get the probability of us having the disease, given that we got a positive test result. Let's do that now. Notice in the numerator, we've substituted in the conditional probability of B given A, which is 0.98, times the probability of A, 0.0001. And in the denominator, we've used the law of total probability to write out the probability of B given A times P of A plus probability of B given A complement times the probability of A complement. When you plug all this in, do the math, notice that you get 0.0048766. So your test is positive and the test is accurate 98% of the time, but the chance that you have the disease is actually less than 1%. Well, I hope you see how you can use amazing techniques like Bayes' rule even in your everyday life. Maybe even the next time you're with your doctor and you get a positive test result, you can sit down with them, pull out Bayes' rule, and calculate the probability that you actually have the disease.